Yeah, so I
Cool.
guess we can start then.
Yeah, we might as well take the extra minute and start. So our first talk today is by David Woodruff. So David's a professor at CMU. So he's worked on a lot of areas in sketching and streaming, especially numerical linear algebra, and especially recently this area of robust streaming algorithms. And he's going to give our first talk of this workshop. And my understanding is he's going to give us sort of a general overview of this area, which will be a nice beginning of the workshop. And then he'll also tell us some of the exciting developments which have occurred. So thank you so much, David. Feel free to take it away.
Okay, hi everyone. I'm David Woodruff, and this talk is about adversarially robust streaming algorithms. I'd like to thank the organizers for putting together this workshop and for inviting me. My talk is based on two joint works, one with Omri Ben-Eliezer, Rajesh Jayaram, and Elon Yogev, and another with Samson Joe. Okay, so let me start off by defining the streaming model. This is a model that has been around for several decades now and was designed to model extremely large data sets. For example, internet traffic, financial transactions, sensor networks, and so on. And given the sheer size of the data set, you would like algorithms that make a single pass over the data and use low memory and compute or approximate a function of interest. Okay, so you don't have enough memory to store the entire data set. This can be formalized as follows. There's an underlying n-dimensional vector x, which is typically initialized to all zeros. For convenience, we're also going to assume that the total number of updates in the stream is bounded by some polynomial in the dimension n of the vector x. Now, what is an update? At time t, we receive an update it, delta t, which indicates that the ith entry of x should be replaced with its old value plus the change delta t. Typically, these delta t's are integers, and we'll assume that for this talk. Now, if for all t, delta t is greater or equal to 0, the stream is called insertion only, which is a model we will largely focus on in this talk. Okay, so the algorithm can't afford to store the entire vector x, so instead it stores a small sketch or summary of the data, which is x, and its memory should be much smaller than n bits. At any point in time, the algorithm might be asked, what is the current value of f of x for some function f of interest? And we'd like to compute this or return an approximation to it using a small amount of memory. Some well-studied example problems in the streaming literature include the second moment f sub 2, which is just the squared Euclidean norm of this underlying vector x, that is the sum of squares of its entries. Another well-studied problem is f sub 0, which is the number of coordinates in x that are not equal to 0. Now, if you're in the insertion-only model, then this just coincides with the number of distinct elements that you see in the stream, because each distinct element corresponds to one coordinate of x, and when you see it, it causes the coordinate value to increase by 1. So f0 is just the number of distinct elements in the insertion-only model. Okay. Let me give you an example algorithm for one of these problems, namely the F2 moment estimation problem I just mentioned. So here the goal is to output an approximation F2 tilde, which is at least 1 minus epsilon times the F2 value, and at most 1 plus epsilon times the F2 value. Recall F2 is just the squared Euclidean norm of x. Here is an algorithm due to Alon, Matthias, and Szegedy, which is very simple. The idea is to choose a random matrix S, which is wide and fat. Namely, this matrix is 1 over epsilon squared, that's the number of rows, by n columns. And each entry is independently set to minus epsilon with probability 1/2 and epsilon with probability 1/2. So here I've drawn S which is just epsilon times a matrix of IID plus and minus ones. In fact, the entries of S can be chosen to be 4-wise independent, which means that S can be stored implicitly with only order log n bits of memory, which is important for a low memory streaming algorithm. The idea then is just to maintain S times X in the stream. This is possible because given an update which says that xit goes to its old value plus the change delta t, we can update our sketch S times X because the new sketch S times X is equal to the old sketch S times X plus delta t times the ith column of S. Okay, so it's easy to maintain this sketch under these updates in the stream. And here the fact that S is linear and does not depend on the vector X makes it particularly useful in streaming applications. At the end of the stream, the estimator is just to output the squared length of S times X. And you can show that this is an unbiased estimator for the squared length of X. And you can also show that the variance of this estimator is at most epsilon squared times the square of the expectation. And therefore, by Chebyshev's inequality, this gives the desired approximation with constant probability. Note that the total amount of space is 1 over epsilon squared times log n bits of memory. This is because we have 1 over epsilon squared coordinates in our vector S times X, and each coordinate requires storing a counter, which is log n bits. Okay, please stop me if you have any questions at any time. Okay, now we are not just interested typically in the value of the function at the end of the stream, but at any intermediate point in the stream as well. So let xt be the stream vector after receiving updates 1 through t in the stream. Then the algorithm is required to output rt at time t, which is its output at that time, and it's supposed to be within 1 plus or minus epsilon of the actual function value f of xt. Now, how does the algorithm interact with the stream? So in the classic streaming model, the way the stream interacts with the algorithm can be visualized as follows. A data center here, which I've drawn as this maybe gray hard drive here, a data center holds the stream and feeds an update it comma delta t to the streaming algorithm, which I've drawn here as someone working on their computer. The streaming algorithm then outputs a response, its output at that time, RT, which hopefully satisfies this guarantee. Note here that the stream generator, this data center, it doesn't get to see the response RT of the streaming algorithm at time t. The stream generator then generates the next update in the data stream, it plus 1 delta t plus 1, feeds it to the streaming algorithm, which then outputs its next response, and so on. Okay, so in summary, in a classic data stream, the data is fixed before the algorithm starts. That is, future data does not depend on the outputs RT that the streaming algorithm is producing as it is processing the stream. But this is often not realistic, since in real life, future data often depends on past decisions. For example, if you have a stream of market trading data and you make a purchase, well, this purchase can influence future market data. And somewhat surprisingly, at least to me, there were previously no guarantees on streaming algorithms in this case. This motivated us to define the notion of adversarial streams. where now an adversary controls the stream updates. That is, the adversary gets to see the responses, the outputs RT, and then it gets to choose its next stream update, IT plus 1, delta T plus 1, as a function of all of the outputs that it has seen so far. Okay, so now the picture is a little bit different. We have a two-player game here, and we see that the data center, or adversary, is going to generate a stream update, I1 delta 1. This is the first update, which is fed to the streaming algorithm. But now the response R1 of the streaming algorithm, the output, is given back to the adversary. The adversary gets to look at this output and then decide on its next stream update, I2 delta 2, and so on. Okay, then the adversary sees R2, and then now comes up with the next stream update, which is a function of both R1 and R2, and so on. Okay, so note that the adversary stream now depends on all responses it has seen so far. And we do not impose any computational limits on the adversary, though you can impose computational limitations and sometimes obtain better algorithms. Formally, in an adversarial stream, the goal of the adversary is to make the algorithm fail to output an epsilon approximation. That is, the adversary wants, at some time t, for the output RT of the streaming algorithm to not be within the desired approximation of the function. That is, RT is not in the range 1 plus or minus epsilon of f of xt. As I said, the adversary has unbounded computational power, and it knows the entire history of outputs, R1 through RT minus 1 at time t. Okay, so how can we design streaming algorithms that are correct in the presence of an adversary? That is, adversarially robust streaming algorithms. Well, one way is just to design a deterministic algorithm. Deterministic algorithms, by definition, are correct on all inputs, and so are correct on whatever inputs the adversary might choose. But most streaming algorithms, to be interesting, meaning to obtain sublinear space, provably must be randomized. Okay, so now when the algorithm reveals its responses, the adversary might learn something about the algorithm's randomness, and this might therefore compromise the algorithm's correctness on future stream updates chosen by the adversary. And this is, in fact, a real issue. Looking at classic sketches, such as the Alon, Matthias, and Segedi sketch that I mentioned earlier for the second moment F2 estimation, it's not hard to show that this sketch is actually not adversarially robust, even in insertion-only streams, meaning that all of these updates, again, the delta t values are non-negative. So this really means that we need new algorithms. Okay, this is a real issue. Now, the main result of the work with Ben-Eliezer et al. Is that we give two generic methods to transform any streaming algorithm A into an adversarially robust algorithm A prime. Okay, so an algorithm that is correct in the presence of an adversary in the way that I defined it, with a mild space overhead. We call these two transformations sketch switching and computation paths. And the reason they're called sketch switching and computation paths will be clear when I explain why and how these methods work. But let me just first mention some properties of these transformations. So both of these methods, sketch switching and computation paths, provide similar results, but differ in the precise overhead in terms of the logarithmic and 1/epsilon factors in the overhead we're going to get over a non-robust streaming algorithm. In particular, sketch switching gives somewhat better bounds when there are existing algorithms for the underlying streaming problem, which are so-called strong trackers. Okay, that is, these are algorithms that are correct at all times in the stream, and they beat the naive log n blowup in the space complexity that can be achieved simply by repeating any streaming algorithm log n times and taking the median of the estimates. Okay, so this is one way of taking an algorithm that is correct at one point of time in a stream and making it correct at all points in time. Just repeat it log n times, suffer that log n factor blow up in your memory, take the median of the estimates at each time. There are many interesting problems in the data stream literature where you can get correctness at all points in time without this log n factor blow up, and sketch switching can give better bounds when you have algorithms which have this property. Okay, on the other hand, computation paths give slightly better bounds when the dependence on the failure probability delta does not multiply the leading order term in the space complexity. Or maybe it does multiply the leading order term, but the dependence on delta is fairly mild. Okay, and this is because the way that we use such an algorithm in the computation paths transformation is we take delta and we set it to be, this failure probability delta, we set it to be something very small, like even less than 1 over a polynomial in n. It's something like 1 over n to the 1 over epsilon. It's actually 1 over n to the 1 over epsilon log n. But the point is, it's something very small. And if your space complexity depends very mildly on this failure probability delta, then this, this leads to a low overhead, adversarially robust streaming algorithm. I should also mention, if the dependence on delta in the time complexity for processing these updates is mild, then you can also get fast processing time. Okay, but let me describe the guarantees of these transformations more formally. And to do so, I need to first define a notion that we introduce, which is called the epsilon flip number of a function. Okay, so here we have a function f from n-dimensional vectors x to the reals r, and the epsilon flip number, which is denoted lambda sub epsilon of f, is the maximum number of times this function value f can change as x starts at the 0 vector and you receive poly n updates to x in the stream. It's the maximum number of times the function value can change by a factor of 1 plus epsilon. Okay, so to give you some feeling for the flip number, if I'm in an insertion only stream and I'm just counting the number of updates that I see in this stream, well, I have 0, 1, 2, 3 out to poly n. How many times does this counter change by a 1 plus epsilon factor? Well, it changes by log base 1 plus epsilon of poly n, right? So the counter changes log base 1 plus epsilon of poly n times. Okay, and this is just order log n over epsilon. And in fact, for many problems in the insertion only model, the flip number is order 1 over epsilon times log n. In fact, for the pth power of the p norm of the vector x, which is just f sub p, the pth frequency moment, we saw this earlier when p was equal to 2, that was f sub 2. So this is just the sum of absolute values of coordinates of x raised to the p. Then you can show for insertion-only streams and constant p, which is what is typically studied, that the flip number is order 1 over epsilon log n. That is, your vector x starts at all zeros. After poly n stream updates, all the coordinates of x are at most poly n, and the pth power of the p norm is at most poly n. And so the flip number is again log base 1 plus epsilon of poly n, which is order 1 over epsilon log n. Okay, so the flip number captures how many times the function changes by a 1 plus epsilon factor, and it can't change that many times in an insertion-only stream, and so the flip number is 1 over epsilon log n. Okay, given this definition of flip number, I can now state, at least in a slightly more formal way, the two results guaranteed by our transformations, the sketch switching and computation paths transformations. So the top theorem here in blue concerns the guarantee offered by sketch switching. Again, we have this function from vectors to real numbers, and let A be any algorithm which epsilon tracks this function f. So all that means is that this is a streaming algorithm which correctly provides a 1 plus epsilon approximation to f at all points in the stream. This algorithm uses some space of A. This is its space in the non-robust setting. Then what sketch switching gives is a new algorithm, an adversarially robust streaming algorithm, A prime, which is also correct at all points in this stream, which is now adaptively chosen by an adversary. And the space of this new algorithm, A prime, is the space of the old algorithm times the flip number of this function f. Okay, and as I mentioned, for many of these problems in the insertion-only model, at least the flip number is order 1 over epsilon times log n. So that would be the multiplicative blowup in the space needed to make your algorithm adversarially robust. Okay, so that is the sketch switching theorem. The theorem that we have regarding computation paths is the following. Let A be any algorithm, again, which is correct at all points in the stream. That is, it epsilon tracks the function value. That is, at every point in the stream, it provides a 1 plus or minus epsilon approximation. Here, the success probability is 1 minus delta. The overall success probability of being correct at all points in the stream. And the space of the algorithm is space of A comma delta. I parameterized it by this failure probability delta. Then there is an adversarially robust algorithm A prime, where the space of this algorithm is the space of the old algorithm, but where you replace the error probability parameter delta with delta prime, where delta prime is delta times n to the minus flip number. Okay, so the idea behind this theorem is we're just going to run our original streaming algorithm, but we're going to replace the failure probability with something really, really tiny. Delta times n to the minus flip number. Okay. So these are the two theorems. And now let me explain the intuition behind the proofs of these theorems and actually how the transformations themselves work, the sketch switching and the computation paths. So I've just repeated the sketch switching theorem above here in blue. It's exactly what it was before. The space blows up by a flip number factor. Again, please stop me or ask in the chat box if you have any questions at any time. Okay, so let's see how sketch switching works. Here is the algorithm. We're going to create roughly flip number independent sketches S1 through Sk. Okay, so k is going to be about the flip number of this function. It's technically the flip number with parameter epsilon over 12 instead of epsilon. There's some epsilon fiddling going on. Each of these sketches is going to provide a 1 plus or minus epsilon over 10 approximation at every point in a non-adaptively chosen stream. Okay, and I want to stress that all of these sketches are going to be run on the entire stream that is seen by the streaming algorithm at any point in time. Okay, so we're going to start by setting the parameter I equals 1. What this means is we're going to be monitoring the output of the first sketch when I equals 1. And more generally, we're going to be monitoring the output of the ith sketch. Also, at initialization, we're going to set the initial output R0 to be 0. This is just because for typically the vector x at initialization is set to be the 0 vector, and typically the value of many interesting functions in the streaming model is 0 on the 0 vector. Okay. We then, at a general time t, and for whatever value I is at time t, what we're doing is we're looking at the estimate produced by this sketch S of I. And we're asking ourselves, is this estimate within 1 plus or minus epsilon over 3? I mean, whatever, these constants are not important. 1 plus or minus epsilon over 3 of the output that we gave the adversary, RT minus 1, at the previous time step. If our new estimate provided by SI is not in this range, then what we're going to do is we're going to set our output RT to be the estimate provided by SI. And then we're going to throw out this sketch SI. The reason we throw out this sketch SI, meaning we're no longer going to monitor it or even update it, we're just not going to look at it at all anymore. The reason we do this is because at this point in time, the randomness of the sketch SI has been compromised. We've revealed to the adversary an estimate provided by this sketch SI. And so at this point in time, what we're going to do is throw that away and set I to be I plus 1. And now we're going to start monitoring the I plus first sketch, meaning we're going to be basing our decisions on the estimate provided by the I plus first sketch. Now, the other case here is that this estimate provided by SI is actually close to what we output at the previous time step, RT minus 1. And in this case, we're just going to output whatever we output at the previous time step. So RT will just be RT minus 1. So what's happening here is that when we increment I, this is called sketch switching, since we're now monitoring the output of a new sketch. When we increment I, we post a new output, and the adversary keeps seeing the same output over and over again until, we're monitoring SI plus 1, and until our estimate provided by SI plus 1 is too far away from what we have been continually giving the adversary. And at that point, we post a new output to the adversary and switch our sketch again. Okay, so this is how the transformation works. But why is it correct? Okay, to see correctness, we're going to argue as follows. Note that both the streaming algorithm and the adversary might be randomized and be tossing coins. Now, if there is a randomized adversary which succeeds in making a randomized streaming algorithm fail, then by averaging, there is some fixing of the randomness of the adversary, which with good probability over the randomness of the streaming algorithm makes the streaming algorithm fail. Okay, this just follows by averaging. This is the easy version of Yale's minimax principle. So without loss of generality, we can assume the adversary is deterministic. Now, why is this convenient for the analysis? Well, this fixes the part of the stream that the adversary is going to feed to the ith sketch right after the previous sketch, SI-1, returned its answer out and was thrown away. Okay, so I want to note one thing here, which is that the stream that the adversary, this deterministic stream that the adversary is going to create right after SI-1 was thrown away, it does not depend on SI because we've revealed no information about SI at this point, though it might depend on all the previous sketches, S1 through SI-1. But at this point, what's happening is the adversary just keeps seeing this output out over and over again, right? So it makes a query. At the next time it sees out, it sees out, it sees out, it keeps seeing out. And the adversary is deterministic. So when it keeps seeing out, it's just going to decide on some stream, some long, you can think of it as infinite length or poly n bounded if you'd like, some long stream, which is what it would produce if it just sees out over and over again. It's a deterministic stream. That's its behavior if it just keeps seeing out. Since this deterministic stream doesn't depend on SI, it's a non-adaptively chosen stream from SI's perspective. It means that SI is correct at all positions in this new stream. Okay, so now SI is going to continue to output this old value out until, now we're monitoring SI, until its value out prime is not within 1 plus or minus epsilon over 3 of this old value out. At which point we then switch to SI plus 1 and we post this value out prime to the adversary. Now, you might worry that you learned something about SI until it outputs out prime. Namely, that its estimate was not outside of this range, 1 plus or minus epsilon over 3 out. And you do learn this, but it doesn't matter as the adversary just keeps seeing out. And so it's chosen its deterministic stream, and this is fixed beforehand. So SI is correct on whatever fixed stream the adversary chose until SI outputs out prime. Okay, so that is the proof of correctness here. But there still remains something to show. We need to bound the number of sketches that we use. If we have too many sketches that we start off with, that are being run at all positions in the stream until we throw away that sketch, then we'd have too much memory. To bound the total number of sketches we need, notice that if SI provides a 1 plus or minus epsilon over 10 approximation, then if out prime, the estimate that it's producing, is not inside of this range, then necessarily F has changed by 1 plus or minus epsilon over 12 factor. Okay, so this follows by correctness of the sketch SI on a non-adaptive stream. But importantly, since this implies that SI has changed by a 1 plus or minus epsilon over 12 factor, this means the total number of times that the sketch can be thrown away can be charged to the flip number, because the function is changing by this number of times. So the total number of sketches we need is proportional to the flip number. Okay. And conversely, to argue correctness, if f indeed changes by a 1 plus or minus epsilon factor, the actual function changes, then you can show that necessarily the estimate out prime is not inside of this range 1 plus or minus epsilon over 3 of the old value out. This again just follows by correctness of this sketch SI on a non-adaptive stream. So we are correct at all times. Okay. Now let me quickly discuss the computation paths transformation. Again, I've just stated the theorem above here that was the same as before, slightly more precise here, that if we have an algorithm A with space L of epsilon delta, then we get a robust algorithm A prime, where the space now is the old space, but you replace epsilon with epsilon over 10, say, and the failure probability delta with now a much smaller failure probability, delta times n to the minus flip number. Okay, so let me explain the idea behind this proof. So the idea is we're just going to run one algorithm now, where we set the failure probability to be very small, just like I had on the previous slide. And by a similar argument, we only need to change the output of our algorithm flip number of times. Okay, so the algorithm might be producing estimates that are changing all the time. But we don't need to output the new estimate every time it changes. And here it is important that we only change the output that we post to the adversary when we are monitoring the output of our algorithm, when the actual output indeed changes by a 1 plus or minus epsilon over 3 factor from what was previously output to the adversary. This is just as in the previous proof. So let me just stress, we don't want to be posting a new output to the adversary every time our output changes, because it might be changing a lot and would reveal a lot of information to the adversary. Rather, we only post a new output to the adversary when we have to. Now, note that the stream length is poly n, and the output for many of these streaming problems can be assumed to be order log n bits. Okay, and since we're just changing our output flip number of times, it's not hard to see that there are only n to the flip number possible streams a deterministic adversary can create. Indeed, the adversary, again, can be assumed to be deterministic without loss of generality. And so it generates a deterministic stream initially. And then it sees one of these outputs of our algorithm. And then it appends a new deterministic stream to what it's already created. And then it sees another output, might append a new deterministic stream, and so on. But since the total number of outputs is the flip number, and there are only poly n choices where the first output can be made in a stream of length poly n, and then there are poly n values, possible output values at that time. Then we have revealed that output, then there are poly n choices where we might reveal the second output, and so on. In total, there are only n to the order flip number possible deterministic streams an adversary could ever create. And so the idea is, well, let's just set our failure probability delta prime to be small enough so we can union bound over all such deterministic streams that an adversary could ever create. Okay, so that's the idea behind computation paths. And now we can instantiate these transformations with known streaming algorithms, and we obtain a large number of results for many important streaming problems listed here. I've listed the FP moments that I talked about earlier, and there are other problems here that I won't define. And what you see, roughly speaking, is that in the non-adversarial setting, you get a 1/epsilon squared dependence up to log factors for many of these problems. Whereas in the adversarial setting, the space blows up to roughly 1/epsilon cubed for many of these problems. Okay. In very interesting follow-up work of Hasidim, Kaplan, Mansour, Matthias, and Stemmer that you'll hear about later in this workshop, they showed how using differential privacy, one could actually improve these bounds. I do want to mention that the connection with differential privacy was also discussed in work with Hart on linear sketches with adaptively chosen queries, though there the result was negative. And here, what this new paper shows is that there's a positive result, that the 1/epsilon cubed bound of this previous work with Ben-Eliezer et al. Can be improved to roughly 1/epsilon to the 2.5 for F0, F2, and many other streaming tasks that I mentioned. And more generally, what the authors achieve is that you can get a blow up of roughly square root flip number for these problems instead of being linear in the flip number. Okay, so you'll hear more details about that later in the workshop. In further follow-up with Joe, we introduced the notion of a difference estimator, which is a new technique for data streams. And I'll give the intuition for this momentarily. But using this concept, we improve the prior 1/epsilon cubed and 1/epsilon to the 2.5 bounds that I just mentioned to 1/epsilon squared, which is optimal for these problems. So for F0, for F2, and all of the other streaming problems that I mentioned, many other streaming tasks. And more generally, what we can get is algorithms for any problem that has a difference estimator, where the blowup is epsilon times the flip number. Okay, and this blowup, well, this improves the previous flip number and square root flip number blowups that I mentioned in the insertion only model for many problems, because as I mentioned, for many important data stream problems, the flip number in the insertion only model is at most log n/epsilon. And in this case, this blowup is much less, and it gives optimal bounds. I do want to mention that non-robust algorithms for these problems already require 1/epsilon squared bits, so our memory is optimal in terms of epsilon, and it often matches the log factors as well for non-robust algorithms. Also, as an aside, difference estimators seem to be a new streaming technique which are useful whenever temporal properties of the stream play an important role. And using them, we're able to resolve open questions in the related sliding window model from Braverman and Ostrovsky, obtaining the first optimal bounds for FP moment estimation for every value of P. So this beats the standard smooth histogram framework, if you're familiar with that, in the sliding window model. And as an illustration of our bounds, you can see that, again, roughly speaking, the first transformation had roughly a 1/epsilon cubed blowup for many problems. This was improved to roughly a 1/epsilon to the 2.5 blowup. And our result here improves it to the optimal 1/epsilon squared. Okay. So how do we get these optimal bounds? What are difference estimators? So the idea in this work is that we ask ourselves if we really need to switch our sketch. So let's look at the sketch switching transformation. If we really need to switch our sketch whenever the output changes by a factor of 1 plus epsilon. Now, what is the answer to that question? Well, maybe. I mean, it's unclear exactly what the adversary is learning. But we could ask this more refined question. If the last output out that was posted to the adversary, that was given to the adversary, was a 1 plus or minus epsilon approximation to a function value f of x. And now f of x changes to f of x prime. Okay, so the underlying vector changed from x to x prime, where f of x prime is within 1 plus or minus order epsilon of f of x. Do we really need a brand new 1 plus or minus epsilon approximation to f of x prime? Okay, that is kind of the driving question. I mean, it seems wasteful. We've already fixed the value out and we've posted it. We've given it to the adversary. So maybe we can somehow use out for something useful algorithmically. And this is exactly the idea behind a difference estimator. The idea is that we can try to approximate the difference f of x prime minus f of x up to a constant factor, constant multiplicative factor, which would suffice because given our promise that f of x prime is close to f of x, it means approximating the difference up to a constant factor would actually give you additive error, which is order epsilon times the function value. So we can try to approximate the difference and then add it to our output out. But how to approximate the difference of two function values, given, say, the promise that these function values are close within epsilon times f of x? It's not clear how to do this in a data stream. Now, what could you naturally try? Well, we can't afford to separately approximate f of x prime and f of x, each up to a multiplicative 1 plus or minus epsilon factor. This would just degenerate to the techniques that I've already discussed and would give a 1 over epsilon cubed dependence. On the other hand, we can't separately approximate f of x and f of x prime up to a constant factor either, because then the difference might be off by a constant factor times f of x. And so the additive error is not epsilon times f of x. So it seems like we need genuinely new techniques for designing difference estimators in data streams, which have not been studied. As an example, when this function f is the squared 2 norm, this f2 that has been our running example, then the difference of the two function values would be the squared length of x prime minus the squared length of x. And there's a very nice algebraic relationship here that this difference is the squared length of x prime minus x plus twice the dot product of x prime minus x and x. And so we really just need to approximate this right-hand side if we want to approximate the difference. And we only need additive error epsilon times f of x. And it is possible to do this actually with only 1 over epsilon memory instead of the 1 over epsilon squared memory that we were using previously. So you can use random matrices with 1 over epsilon dimensions. I won't get into the details, but it is possible to approximate this right-hand side. Now, you can't simply use a difference estimator for each successive difference in your stream, because each time you're incurring epsilon f of x additive error. And so if you just use a difference estimator every single time, then these additive errors would accumulate, and you would end up, after 1 over epsilon applications, you would end up with constant factor additive error. So I won't describe it here, but instead the idea is one can organize these difference estimators into a binary tree-like scheme to build the overall algorithm so that you only have to take log 1 over epsilon differences at different scales. So this is, a way of avoiding this, additive error increasing to a constant factor times the function value. We do need to run many difference estimators in parallel, as in the sketch switching paradigm. And we also need to build difference estimators for many different functions. And here for F2, there's this fairly simple relationship that I've written here that drives the difference estimator. For other functions, it's often more complicated. And finally, my last slide, let me just mention some other follow-up work that you will hear about later in this workshop due to Kaplan, Mansour, Nissim, and Stemmer, which is that they exhibit a problem in the insertion-only model for which any adversarially robust algorithm requires a blowup of square root of the flip number. So this doesn't hold for the problems that I mentioned. It would contradict these no overhead upper bounds that I just mentioned in this follow-up work with Joe. But it holds for this problem that they construct. And it shows in general that this root flip number dependence is best possible if you look at all problems. For appropriate parameters, this gives an exponential separation for this problem. If you set the flip number for their problem appropriately, then you get an exponential separation in the amount of memory needed to solve their problem for adversarially robust versus non-robust algorithms. So we can't hope to have no overhead for all problems, though we see that for many important problems that just have difference estimators and small flip number in the insertion-only model, we can get optimal algorithms. An important open question is what happens when you have many insertions and deletions? Can you get optimal algorithms in that case? Or what is the best possible separation? And maybe these techniques can shed light on many of the standard problems in data streams when you have both insertions and deletions. And so with that, thanks for your attention, and I'll stop here.
Thank you very much. We have a relatively short time for quick questions. So a couple of quick questions if you want to ask.
This might be obvious. I have a quick question. This might be obvious, but the issue with insertions and deletions is because the flip number, is that because the flip number gets really big? Is that the main problem?
Yeah, you can just insert something and then delete it, then insert it, then delete it, and then, yeah, the flip number can just go back and forth with every, the function can change by a multiplicative constant factor with every single update, yeah.
And then like a related question is, I guess it's partially answered by this follow-up work, it sounds like, but are there any like natural problems where the flip number is large, but they still have small space complexity in streams?
Where the flip number is large.
Let's say the insertion-only flip number is large, but they still have efficient streaming algorithms.
Efficient, robust streaming algorithms with a large flip number. Yeah, so none of these problems in the insertion-only model, these natural data stream problems, so these natural data stream problems, they all have a flip number that is roughly 1 over epsilon log n, and we get a dependence of like epsilon times that, and it kind of erases the epsilon dependence in the space bound. And so for all these natural problems, the flip number is already small. Yeah, so I'm not aware of a problem that has that behavior, but that's a good question. Yeah.
Cool, thanks.
Yeah, thanks.
Can I ask one very quick question?
Yeah, Sayan.
Thanks. So the question is, in the fully dynamic setting, where the flip number can be very large for even one of these standard problems, is there any strong lower bound known which says that you cannot do well against adaptive adversary?
No, so this is an important open question that I mentioned, right? So for F2 estimation, for example, the flip number can be very large in this fully dynamic model, right? And this technique using differential privacy gives a square root flip number dependence. But this lower bound where you require a square root flip number dependence, which you'll hear from later in the workshop, doesn't apply to this problem, at least. Yeah, the current results that I know of don't apply to these natural problems in the fully dynamic setting for natural problems. Yeah.
I see. Thanks.
Yeah.
I have a quick question. So for the distinct elements problem, is the adversarially robust bound 1 over epsilon squared times log n, or is it 1 over epsilon squared plus log n, just like the non-robust model?
Yeah, so one thing I didn't mention is you can actually get overhead, which is just a constant factor if you make strong cryptographic assumptions. So I did mention there's a possibility of making these assumptions on the adversary to get slightly better space bounds. If you do that, you would only get a constant factor overhead. Information theoretically, we're getting in this follow-up work, we're getting 1 over epsilon squared times log n, but I think, yeah, I'd have to check. I'm not sure if we tried to optimize this. So the information theoretic bound, are you asking like, can you get 1 over epsilon squared plus log n information theoretically?
Yeah.
Yeah, so I think we're getting log n over epsilon squared, and I'm not sure if this can be optimized. I forget actually if we did it for this. So for many of these problems, what you can do is instead of having log n sketches, you can have log 1 over epsilon sketches, and you just start a sketch at a certain point in time. And I mean, so you don't need flip number of sketches because you can throw away the prefix of the stream. If I throw away a prefix of epsilon fraction of distinct elements, then it doesn't affect the overall estimator by a 1 plus epsilon, by more than a 1 plus epsilon factor. And so therefore, this is one way of getting rid of that log n, which is just to, instead of running log n sketches in parallel, you run log 1 over epsilon sketches in parallel. And so I think this actually does work for F0 estimation.
I see. Thank you.
Yeah, yeah.
Okay, so I guess our time is up, and thank you very much again, David, and thank you for those who asked questions. Our next speaker will be Yuval Dagan, who is a graduate student at MIT, who is working on online learning, on learning theory topics, and in particular, in this talk, he will connect between adversarially robust sampling and online learning.
Hey, thanks for inviting me. So this talk will be about adversarial sampling algorithms. And this covers both a joint work that I was having with Omri, Eilon Yogev, Shai Moran, Moni Naor, and Noga Alon, and also the work that introduced this this notion, which is by Omri and Eilon. So I will talk about sampling algorithms. And these algorithms receive an extremely large amount of data, but they don't have enough memory to or enough resources to process all this data. So they will sample a small fraction of it, and they will analyze only this sample. For example, you can analyze internet traffic, financial transactions, sensor networks, etc. So here is the definition of sampling algorithm. So we have a statistical analyst that receives a stream of elements. And for each element, they decide whether they want to store it or discard it. Now, the analyst only has access to the sample, and it is very small compared to the stream. So the classical assumption in streaming algorithm is that the stream is fixed a priori. However, this assumption is not realistic in many scenarios, in particular when the analyst continuously interacts with the outside world. For example, an online store will analyze the transactions, and based on that, they will decide on their inventory, and thereby they are influencing the future transactions. And network devices send the networks, and based on that, they route new packages, thereby they also influence the network. So we want to assume a more robust setting. So that's the model that we will be discussing. And here we assume that the stream is generated by the adversary. And we make a strong assumption that the adversary knows exactly what elements are sampled. And based on that, they decide on what elements to stream. So let's see what sampling algorithms we considered. So we will actually analyze very simple sampling algorithms that just sample a random subset of the element. So first of all, we have the Bernoulli sampler that will just decide on each element independently whether they want to sample it. And we also have the uniform sampler that will just sample a fixed random set of coordinates out of the stream of fixed size. And the most sophisticated sampler that we will analyze is the Reservoir Sampler that will maintain a sample of constant size throughout the stream. And this will enable the analyst to get good analysis throughout the stream. And this requires also removing elements from the stream. So there are multiple reductions also between these samplers. And for the purpose of what was studied, there are, in fact, all of them are equivalent. So what is the goal from the sample? So what was studied is the setting that you want to collect multiple statistics out of the stream. For example, a shopping store would like to know how many transactions were made in New York City. They would also like to know how many STOC 21 souvenirs were sold, etc., etc. And network adapter would like to know what is the congestion along each link. And these all correspond to estimating multiple statistics of the stream. So here is the formal model. So we have multiple statistic functions. I call them the FIs. And we want to know the average of each of these statistic functions on the stream. But we only have access to the sample. So we will use the sample average instead of the stream average. And we want to get all of these statistics correctly. So our error will be just the maximum over all the statistics of the difference between the sample mean and the stream mean. And we would like to get this error below some parameter epsilon with probability 1 minus delta, where the stream is adversarial, but delta is just a parameter that depends on the randomness of the sampler. So what can be done in the static case, in the classical streaming setting? So here, actually, it is sufficient to collect a sample of constant size. In fact, the constant is the VC dimension of the class of statistics that you want to approximate. And this just follows from standard results in learning theory due to the fact that the stream is fixed and you just pick a random sample out of the stream. And the natural question to ask is whether in the adversarial model, it is also sufficient to collect a sample of size VC dimension. And let me give you an example where this actually does not hold. So here we have a stream of real numbers, and we just want to approximate its empirical CDF. And we want to do it in L infinity distance, namely at every point. So in particular, we want to collect a sample whose CDF will be epsilon close in L infinity to the one of the original stream. And this exactly corresponds to approximating multiple statistics of the stream because we just want to know what is the CDF at any point. And this corresponds to just asking what fraction of points fall below some threshold A. So we have multiple statistics, which are threshold functions that we want to approximate. And actually, the collection of threshold functions has a VC dimension of 1. So in fact, in the static case, a constant size sample would be enough. However, this is not the case for adversarial streams. So in fact, no sampler would succeed in this task. And let me show you what the adversary can do. So first of all, the adversary will show some point. And if this point was sampled, then the adversary will show a smaller point. If it wasn't sampled, they will show a larger point and continue this way. And the adversary maintained the fact that all the sampled points are greater than the non-sampled points. And in particular, the sample CDF would not be close to the stream CDF in L infinity distance. So this seems like a major issue, but and indeed it shows that the adversarial setting is harder than the static setting. However, if we assume that the points have a fixed precision or a finite precision, then we can actually also compute the CDF in the adversarial setting. So let me show you now the positive results for the adversarial setting. And I remind you that we have a class of statistics, and we want to approximate all of them using the sample. So the simplest bound is just tells you that the sample size can be order of log the number of statistics that you want to approximate. And an improved bound shows you that, in fact, you can do better. And the sample size can be order of Littlestone's dimension of the class of statistics. And now Littlestone's dimension is just the analog of VC dimension in the online learning. So in fact, the sampling error will corresponds to the error in online learning. And there is also a lower bound, or omega of Littlestone dimension, but the bounds are not tight in terms of the parameters epsilon and delta. And this is true for binary valued statistics. And for real valued classes, there is also a bound that I won't get into. And this is by the sequential shattering dimension of the class. This is a generalization of Littlestone's dimension, but I won't get into that. So we have a bound on the optimal sample size in the adversarial setting. And now let me mention another task that you might consider. And this is called tracking. So here we want the analyst to maintain a correct sample at all times throughout the running of the stream. And this, in fact, can be done if we use the Reservoir Sampler. And this, as I mentioned, this is a sampler that maintains the same sample size at all times. And the overhead here will be on the sample size would be log the stream length. And this is also tagged. So that's about tracking. And let me now mention other applications to algorithms where estimating multiple statistics doesn't show up immediately. So for example, if we want to learn the median of a stream, then we can estimate the whole CDF. And as we said, this means estimating multiple statistics. And this can be done if we have a finite precision. And we can also estimate quantiles or high dimensional center points. And another classical example in streaming algorithms is heavy hitters. And here you want to know exactly what elements appear at least some constant fraction of the time. And this can also be done using estimating multiple statistics. And in particular, we take as statistics as singleton functions. These are functions that equal 1 on one element and 0 on the remaining elements. And in fact, the set of all such statistics have a Littlestone dimension 1. So we can do heavy hitters with constant sample. And there are other examples for clustering, range queries. There is a whole big notion of statistical query algorithms. These are algorithms that utilize statistics about the data. And in fact, most learning algorithms are statistical query algorithms. These also utilize statistics. And we can also think of learning from a stream by sampling from it. And lastly, let me mention another application to distributed databases. So here we have a database that is distributed across multiple servers, and the data is split randomly between the servers. But we want each server to contain a truthful idea of the reality. And notice that servers can see a lot of adversarial attacks and they influence the outside world. So we need robustness in order to argue that. OK, so that is for the applications. And now let me say a few words about the proof. So the first part of the proof bound the error in terms of a different notion that is called discrepancy or sequential Rademacher complexity. And the second part bounds this quantity. So let me tell you what is online discrepancy. So here we have an algorithm that receives a stream, and it just colors each stream element with either blue or yellow. And now we ask what is the discrepancy of the set of statistics with respect to this coloring. And this will be just the maximum discrepancy over all the functions, namely the maximum over all the functions of the difference between the blue sum and the yellow sum divided by n. So the discrepancy is small if all functions are blue and yellow are kind of equal. And now the sequential Rademacher complexity is just the average discrepancy taken across random partitioning to blue and yellow. And notice that this sequential Rademacher complexity, in fact, really corresponds to sampling half of the elements out of the stream. So it corresponds to sampling each element with probability half. So in fact, what this shows is that instead of considering sampling from a very large stream each element with small probability, we can instead consider a smaller stream where we just sample each element with probability 1/2. And let me show you how this reduction works. So recall that the error that we have is the maximum over all the statistics of the difference between the mean on the sample and the mean on the stream. And let's call the sample blue. So now what we will do for the proof, we will condition on the stream, and then we will randomly draw, just for the proof purpose. It doesn't interact with the adversary. Just for conditioned on the stream, we will sample a new yellow sample. Now, because we conditioned on the stream, the new yellow sample sees a static stream. And we can apply classical analysis to show that the yellow sample actually approximates the stream. So because the yellow sample approximates the stream, it is now sufficient to bound the discrepancy between blue and yellow. And in the next step, I will just remove all the remaining stream. And this way, we just reduced to a stream that is just twice the size of the sample. And this roughly gives you the sequential Rademacher complexity. One needs to do a slightly more reduction, but this essentially gives you the sequential Rademacher complexity. So now I showed you how to essentially reduce the size of the stream and end up with the sequential Rademacher complexity. And the second part of the proof corresponds to bounding this quantity. So again, we have the expectation over maximum over all the statistics of the discrepancy of this statistic. Now, how do we bound this quantity? So actually, for each statistic individually, we can use Azuma's inequality for martingales to show that it concentrates with high probability. And then if we take a union bound over all the statistics, we get the simplest bound, which is logarithmic in the number of statistics. And this gives you an error bound of square root log the number of statistics divided by the sample size. And this gives you a logarithmic sample complexity. So yeah, in the second step, we bounded the sequential Rademacher complexity by just considering each function separately and taking a union bound. And in order to get the second bound, there is a more sophisticated approach. And actually, you can see the more sophisticated approach in the video that I gave in this conference. So let me summarize. So we discussed the adversarial sampling model. we said that our goal was to approximate multiple statistics. We said that adversarial is actually requires more sample than the static case. And we said that the optimal sample size is roughly Littlestone's dimension, which is bounded by log the number of statistics. I also discussed a tracking algorithm that keep the right answer at all times. And I discussed applications to algorithms that are not exactly, do not exactly correspond to compute multiple statistics. Now, for the proof, we did a reduction to the sequential Rademacher complexity, essentially reducing the stream size. And then we bounded it using a union bound and a Zumann's inequality. And let me move to the open problems. So the first problem asks, okay, now let's say you have a general function computed on the stream. The question is whether can you compute it, whether you can approximate it using a small sample in the adversarial world. And this generalizes this would generalize many of the results that I showed you. And we can also study other adversarial models. So we assume that the adversary knows exactly what is a sample, but we might be able to assume less. We might be able to hide the sample. For example, it's possible using differential privacy, and there's a talk about that also. And also, so we just analyzed very simple algorithms that even don't look at the elements. They just randomly select what to sample. But it might be possible that the dependence on the parameters epsilon and delta can be improved if in some cases, it's not always possible, but in some cases it is possible to improve it using a more sophisticated algorithm. So the question is, what are the best algorithms? So these are the main open problems, and thanks for listening. I will end here.
Thank you very much, Yuval. So I think we have time for one question. So I actually have one question about the relation between sequential Rademacher and new online discrepancy results that we've. So for example, one of the best student paper awards in this talk was awarded to some breakthrough results in online discrepancy, and I'm wondering whether it's any related.
So I think in standard, wait, let me move to describe. So what they assume is that I think that the function class f is not known ahead of time. So the function is kind of computed on the fly. That's my understanding. Usually, yeah, in discrepancy, you don't have a fixed set of functions that you want to bound the discrepancy of, but they are kind of given to you in an online fashion. In fact, you don't get elements; you just get values, and you just get the f of xi. But yeah, these f of xi's are not taken from some family.
Thank you.
So
Okay.
I think it might be good to have a short 5-minute break, maybe a little bit less. So I guess just people have a little bit of a break before the second half of our schedule today. What do you think, Omri?
Yeah, so I think let's take a break until 10:35. So it'll be 5
Sure.
minutes back to the schedule. Yeah. So yeah, so see you soon at 10:35.
10:35. Yeah.
Any Omri.
Alan. Okay, so I think we can start. I'm very happy to introduce Chaim Kaplan. Chaim is a professor at Tel Aviv University, and his research is very versatile, and he has had many significant contributions in several fields, including data structures, algorithms, computational geometry, and recently also machine learning. And today he's going to tell us about how we can use the notion of differential privacy as a mathematical tool in order to design new adversarially robust streaming algorithms.
Okay, thank you, Uri, and thanks for organizing this workshop and inviting me to speak here. It's a pleasure to do this. As Uri said, I'm going to talk about how to get adversarial streaming algorithms using differential privacy. This is a joint work with Uri, with Avinatan Hasidim, Ishai Mansour, and Yossi Matis. So I'm going to use the same setup basically that David used in the first talk of this workshop. I'm going to assume that the stream is of length m. You see my pointer, right?
Yep.
Okay, great. So the length of the stream is m, and the domain is n, and the stream is a sequence of updates, right? Which each update is a domain element and an increment. So you can think about a vector being maintained implicitly. The vector, each coordinate in the vector corresponds to an element of the domain, element number one, and each update sort of changes the coordinate of this vector. The u is the index of the coordinate, the name of the item. You can think of the index of the coordinate to be the name of the item, and the delta is by how much to change it. Could be positive or negative in general, and if it's only positive or no negative, then we say that this is an insertion-only stream. So each UI is a domain element, and delta I is the weight change. And at each point in time, after seeing a prefix of I updates, I want to spit out an estimate of some function of this prefix G. So usually the function depends just on the vector. And since I want the space to be sublinear, then I won't be able to maintain this vector and spit out the estimates exactly. So I'm going to, the streaming algorithm, the task of the streaming algorithm, the goal of the streaming algorithm is to spit out an estimate of the value of this function applied to the prefix of the stream up to an accuracy of an alpha. Within 1 plus minus alpha. David used epsilon for this alpha. I'm using alpha because epsilon is going to be the epsilon of differential privacy that will show up soon. Okay, so it's exactly the same setup. Here is an example. This is a domain element, and this is the delta. And say the function G just counts the number of distinct elements in the stream. Think about it. This is the number, in general, it's going to be the number of non-zeros in the vector. And so after these two updates, there are 2 non-zero coordinates in the vector. After this update, there are 3, so I need to report 3. And here, the pink guy goes down to 0, so we are back to 2. And at the end, this is the state of the vector, so there is only 1 element which is non-zero in the vector. And in general, you can think about many other functions G's, like the frequency, the sum of the squares that David talked about a lot. Maybe we want to spit out some statistics, something about the heavy hitters, the largest guy, and many others. Okay, so this is a continuously reporting streaming problem. So I'm reporting an estimate of a scalar function of the prefix of the stream at each time. And many streaming algorithms, have been developed over the years, and many of them are randomized. Essentially, if you want to be sublinear, often you have to be randomized. So if, for example, if you want the sum of squares, then with randomization, you get this 1 over alpha square log m memory that David also mentioned. But if you want to do it deterministically, the space has to be linear. And so most of the algorithms are randomized. And then the usual setting is that you have this randomized streaming algorithm, and you fix the stream, the entire stream, ahead of time, independently of the algorithm and what it's going to do. And then you feed the algorithm with each update, and the algorithm spits out the estimate, the value, the estimate to the value of G applied to the prefix of the stream. And these updates are independent of the coin flips of the algorithm. Now, in this new adversarial streaming model that has been attracting attention, and David also defined, there is an adversary that is playing against the algorithm. It gives it an update, sees the response, and then decide on the next update based on the feedback, potentially based on the feedback that it gets. So this is the setup. So there is you can think about it as a two-player game between a streaming algorithm and an adversary. And the adversary chooses an update for the stream, which can depend on all previous stream updates and the output of the algorithm. The algorithm processes the update and needs to spit out its estimate Zi at each time step I. And the goal of the adversary is to make the streaming algorithm output an incorrect response. And usually it tries to do that by discovering the internal randomness that the algorithm is using. And as we had seen in the previous talks, most classical randomized streaming algorithms, which were designed for the regular oblivious models, are not adversarially robust. You can attack them and fool them if you can pick the updates based on their responses. And the goal is now to design an algorithm which would be adversarially robust, would be resistant to this kind of attacks. So most of this previous work has been already mentioned, so let me just briefly go over it. This is maybe the first one in which Hard and David showed that if the algorithm, the streaming algorithm is linear, which essentially means that the streaming algorithm maintains a projection of these vectors over the domain that I have drawn in the previous slide, then you cannot make it an adversarially, you cannot make it, such an algorithm would not be adversarially robust. And then there is this result that David talked about a lot of Ben-Eliezer, Jayaram, Woodruff, and Yogev, in which they give these general transformations that the performance of this transformation depends on this flip number. Let me just recall what is this flip number. If anyone here didn't attend the first talk, then this is an important parameter that plays in almost all the positive and negative results that exist to date. So you have a stream of length m and a function g, and the flip number is the maximum number of times that the value of g, so you apply g to every prefix of the stream, and you track the value of g as you progress. And you want to see how many times can g change by a factor of 1 plus minus alpha, multiplicative factor of 1 plus minus alpha. So the maximum times that g can change by a factor of 1 plus minus alpha over a stream of length m. This is going to be this flip number lambda, which depends on alpha, m, and g, but I'm going to just abbreviate mostly in some slides and say lambda. And as we have seen, if the stream is, if the model is simple, there are just insertions, no deletions, then often this lambda is about 1 over alpha times log of the length of the stream. And the transformation that we had seen in the first talk takes an oblivious streaming algorithm and makes it adversarially robust with an overhead, space overhead of lambda. So this is the space of the oblivious streaming algorithm, and the transformation that we had seen in the first talk gives us an obliviously robust streaming algorithm that can play against an adversary that tries to attack it, and the space blows up by this flip number. If the flip number is small, like in this situation, the blow up is small, but if we allow insertion and deletion, that this could be as large as the length of the stream, basically, and then we get something which is not sublinear at all here. And this is what I'm going to try to sketch for you. This is what we did. So we came up with another transformation whose dependency still, this is the, I repeat here the definition of the flip number. So it's the performance of our transformation also depends on the flip number, but not, so you see, we multiply by the square root of the flip number, not by the flip number. This is the overhead. So we take an oblivious streaming algorithm and we transform it into an adversarially robust algorithm. And the space is going to blow up essentially by a factor of square root of lambda. There is an additional log factors over the previous transformation. And we, the interesting thing, maybe the most interesting thing in this transformation is that we use differential privacy as a tool. And so differential privacy, for those of you who may have not seen it, is a mathematical definition for privacy that aims to enable statistical analysis of data set while providing strong guarantees for individual level information. I'll give you the definition and some intuition on the next slide. And the last thing I'm going to say here is that I'm going to reiterate what David already mentioned, that there is a follow-up work that came after we published this result, in which David and Zhu also give a transformation, and the blow-up here is alpha times lambda, which, as David said, if lambda is about 1 over alpha, then essentially the blow-up is a constant. So for some problem, this is better than our bound. So they are essentially unrelated. It depends on the flip number, whether in alpha, whether this one would give you a better algorithm or this one. Okay, so before I show you the algorithm and try to outline the proof, let me just say a few words about differential parts. So this is the definition. A randomized algorithm is epsilon delta differentially private. There is an epsilon and there are these two parameters in the definition. And if for every pair of data set that differ on one data point, so S and S prime are two inputs which are identical except of a single point or a single item or a single record, then the algorithm would be differentially private if for every possible outcome, the probability to get this outcome, this could be a set of outcomes, the probability that I get an outcome in F when I run on S, and the probability that I get an outcome in F if I run on S prime are sort of very close to each other. The difference could be up to a multiplicative factor of e to the epsilon. If epsilon is small, this is about 1 over epsilon. And there could be an additive error as well, an additive difference of delta, which usually we think about as very small. So essentially, it means that if you run on S and you run on S prime, you get more or less, each output is being produced more or less with the same probability. So the intuition is that if you know the data set, the entire data set, except of my data point, or my private data, and you also get to see the output of the algorithm, then you won't be able to tell if what was my data. if I was present in the data set at all or not. So the data, think about the input as containing data. Each point in the input is data that belongs to an individual, and an adversary knows all the rows in the data set except for my data point. And we run this differentially private mechanism and make the result public. So now the adversary knows Z as well as every element in the data set except of my data. And this means that statistically, we will not be able to tell what was my data point, even if it has all this information. So this is differential privacy. And now there is one important property of differential private algorithm that we essentially exploit in this transformation, and it is the generalization properties of a differentially private algorithm. And let me try to tell you what's there. So this is maybe the most important slide, because this is the main thing we take from differential privacy. So we all know that if you there is a domain X and there is a distribution over the domain, and you fix a predicate that maps each domain element to 0 or 1, essentially picks a subset of the domain elements, and you want to estimate, if you want to estimate the expectation of this predicate over the distribution, then you can take a sample, and the empirical average of the predicate over the sample is going to be close to the expectation by just usual Hovding Chernoff bound if the sample is sufficiently large. Say if the sample is of size 1 over epsilon squared times log 1 over delta, then these are going to be close up to an additive error of epsilon with probability 1 minus delta. This is standard, right? If you pick a predicate, I give you a sample, then you can take the empirical average as an estimator to the real average of the predicate over the distribution. But if you do a different experiment, you still have a distribution. I take a sample, I give you the sample, and then you pick the predicate by running some computation, some algorithm on the sample. So now here the predicate was independent from the sample. Here you compute the predicate based on the sample. Then this collapses, right? I mean, you cannot, if this is the situation, then you cannot say anymore that the empirical average would be necessarily a good estimator for the real average. For example, you can look at the sample, define a predicate which just says 1 on every item in the sample and 0 for every other item, then its empirical average is going to be 1, but the real average is unrelated. So this estimation thing crucially depends on the fact that the predicate is picked independently from the sample. But here's the thing. I repeat, let's go back to this experiment, but now we still compute the predicate by running some computation on the sample. So the predicate is going to depend on the sample. But if this computation that we run on the sample is differentially private, so I don't compute the predicate by just an arbitrary algorithm running on the sample. I run a differentially private algorithm on the sample. The differentially private algorithm computes a predicate, and then I get back this property. So this is a theorem that was proved and refined by all these guys here, Work et al. And CD tab, that says that if the predicate is picked by a differentially private algorithm, then the empirical average is going to be a good estimate of the real expectation of the predicate over the distribution with about the same size sample that we use in the regular set. Okay, so this is the strong property of differentially private algorithm that we exploit. Okay, so now let me tell you how we prove. So I'm going to outline the algorithm transformation. This is our result. We take an oblivious algorithm, just recall, and turn it into an adversarially robust algorithm with a square root flip number blow up in space. And the high level idea is to protect the internal randomness of the Oblivious algorithm that the adversary tries to attack, to hide it from the adversary using differential privacy. I disconnect the adversary from my internal randomness by doing some private computation. And just please note that I use differential privacy here is not used to achieve privacy, right? I mean, my goal is not to get a private streaming algorithm. I just want an adversarially robust streaming algorithm. So I use differential privacy as a tool to get adversarially robust algorithm by using it to protect the internal randomness of the streaming algorithm. This is the high-level intuition, and this is the transformation. So I'm just making the life a bit easier here, and I switch the flip number. The square root flip number became square root of the length of the stream here. I just assume that the flip number is m for now, and the maximum possible, and then I'll tell you in a few words, if I have the time, how to refine this square root of lambda. And if this is the case, what I do, this is the Oblivious streaming algorithm, right? The Oblivious streaming algorithm, what it does, it takes k, it takes about square root m random strings, and it instantiates k instances of the Oblivious streaming algorithm. So it takes an Oblivious streaming algorithm as an input. It instantiates k square root m, in this case, copies of this algorithm, each one with a different randomness, with a different set of random bits. This is R1 is the random bits that I feed to A1 and so on. And now I start processing, this is the initialization. Now I start processing my stream. I receive the next update. I insert the update to this square root m algorithm. Each of them gets the update and updates its estimate, right? Each algorithm gets an update. In each time step, you get an update. You spit out an estimate of the function g. So I feed these k square root m algorithms by my update. I get their estimates. And then this is the crucial part. I take all these estimates. I privately compute, differentially private, I run a differentially private median computation here that gives me the median of these guys, and this is what I return. And the claim is that this is adversarially robust. And you can see immediately that this is the blow up in space, because I just have square root m of these guys, right? And how does the analysis go at a high level? Let me say 2 words on this. So this algorithm, which I call B here, and I take A and I get B. This is B, the box. So B is differentially private with respect to the collection of the random stream. Because I run the private median computation here, it means that if you change one of these random strings, then the output should not change by much, because the algorithm is differentially private with respect to these strings. So replace a random string, the output should stay more, I should get the same outcome with more or less the same probability. So now fix a prefix of the stream and let A of randomness and this prefix denote the output of the Oblivious streaming algorithm when I run it with the randomness R. So this is a function. So now I define the following function of the randomness. This function takes a prefix of the stream and a randomness, and it's a predicate actually. This function is a predicate of the randomness, and the function is 1 if when I run the streaming algorithm with this randomness on the prefix UI, it gives me an accurate estimate. So I map each random string, which gives me a good estimate, goes to 1, and the other goes to 0. So this is a predicate defined over the random strings. And now I'm going to observe, because this is a differentially private algorithm, and this function was defined based on the output, essentially on the output. The output is the z, but these u's are computed based on the z. So essentially the f the F is also differentially private because I obtain it as a post-processing of a differentially private algorithm. So this is actually a differentially private. I computed this function in a differentially private way. And then I can use the generalization property of differential privacy and apply it to this function. And basically what I would get that if I look at the expectation of this function over the randomness, so assume a uniform distribution over all these random strings. And this is the expected, the expectation of the predicate over this distribution. Basically, it's essentially the probability that the oblivious streaming algorithm succeed on UI. This is what this is. And this is more or less the empirical average over these random strings that I sampled because the predicate was computed in a differentially private way. Here, I'm using this inequality follows from the generalization property of differential privacy that I've outlined in my previous slide. Okay, so now, because I know that the oblivious streaming is good, I can assume that this is close to 1, right? The streaming algorithm, the oblivious streaming algorithm succeed with probability close to 1. So now I know that the empirical average, which is basically the average of these y's, the fraction of the y's that sort of are accurate is close to 1, right? The generalization property of differential privacy gives me that most of these y's, because the expectation over the distribution is 1, I know that the average. So if think about this says 1 if the corresponding y is accurate. So this is just the fraction of the y's which are accurate. So what I get is that most of the y's are accurate, and therefore the median is going also to give me an accurate y. This is why this algorithm actually gives me. So most of the y's are here within a 1 plus minus epsilon of the real value of the function. So the median would also be here. So if you want to quantify what happens here a little bit further, then if B is epsilon differentially private, I omitted the delta here, then this implies the epsilon affects the generalization. So the gap between the empirical average and the real average is epsilon. When epsilon gets smaller, they get closer. So what I want to do, so this algorithm needs to be epsilon differentially private for some constant epsilon, say 1/10, right? And to get that, I have to, so here I do this private computation m times, and I want that all these m computation would be differentially private with the differential privacy parameter of 1/10. Then each of them, this is follows from composition theorem for differential privacy. Each of them has to run with a much smaller privacy parameter that I have to scale down my target epsilon by square root of the number of private computations that I do. Okay, and this means this is why I have to pick this k to be about square root of m. So this is sort of the explanation of why the space blow up. For those of you which are more familiar with differential privacy, so you know that if you do private computation m times, then you need to scale down your epsilon by square root of m, which means that your error blows up by a square root of m. So to succeed here, you need to take the median of at least square root m, guys. Okay, so let me just wrap up here. To turn this result to be a square root lambda here, I need to change this. This is a typo. This should also be about square root lambda. And I need to combine everything that I told you with another technique from differential privacy, which is called the sparse vector techniques, that basically try to take some of the ideas that you have seen in David's talk. So I try now to identify the timestamps I in which the output is still good. So as long as the output does not change substantially by more than 1 plus epsilon factor, then I can keep my previous, I can spit out again my previous output and don't expose any new information to the adversary. So this technique allows me to identify these time steps in a differentially private way and avoid doing this private median at every time step, but thus I would just do it about flip number many time steps. And this would reduce the blow up to be square root of lambda. Okay, so just to wrap up, this is what we have seen in transformation that takes an oblivious algorithm, oblivious streaming algorithm for a function G, and gives you an adversarially robust for G using this place blow up. And as David said, lambda is typically small when there are no deletion, but if there are deletion, it blows up and quickly it becomes linear in the length of the stream. And with our result, you can still get a sublinear algorithm even in this situation. Right? For example, this sum of square thing that we talked about a lot, if you allow deletion, the flip number here is going to be linear. But our transformation would still give you sublinear adversarially robust algorithm, which you couldn't get with the previous one. And there are many open problems in this field. There are gaps between the upper and impossibility result is currently for a somewhat artificial problem. Omri is going to talk about it right after my talk here. So you can try to close the gaps between the upper and lower bound for many streaming problems. And maybe an interesting question that haven't been mentioned, I think, is so all this framework that you see, that this dependency on the flip number and this series of results that improve the dependency on the flip number, they are all limited to algorithms that spit out streaming algorithm that continuously report a scalar. But there are many streaming algorithms that are randomized and do not report a scalar value. They report something else, like maybe a matching, maybe some other configuration or multiple scalars. And then this technique sort of does not apply, at least not obviously apply. And we strive for other techniques that would capture such situations. So I think I'm stopping here, not to run over here, unless there are questions.
Thank you, Chaim. So I guess we have time for one quick question and then move on to the next talk, where the speaker is me.
So you're going to introduce yourself.
Yes.
I have a quick question. I don't know if this is answerable in a short amount of time, so feel free to ignore it. But is there some intuition, like if you think about just the basic F2 estimation case, where this like square root of n actually comes up? Like you're basically taking the median of square root of n trials. Is there some like natural intuition behind why that's necessary in that case? Or
why is the blow up square root of n?
Yeah, like beyond, I guess it's coming from the fact that this blow up in the differential privacy parameter. But
Right.
like if we just like undo that black box, is there some intuition behind why it should show up, say, for F2 estimation? I know it's not, but I mean,
yeah, it essentially follows from composition, the composition theorem of differential privacy. Essentially, in differential privacy, if you want to ask m queries on the same data, and so you keep looking at the same data m times, and you want that the entire sequence of your estimates or outputs would be differentially private, then you need to scale down your privacy parameter by a square root of the number of queries. And if you do that, then the noise blows up by square root of the number of queries. And once you have this amount of noise, then for the median to still be a median, you need to take the median of at least that many data points. So I'm not sure if I can be more intuitive. Maybe Uri can.
No, that makes sense. Or like you would need to understand the intuition to find the composition theorem of differential privacy.
Yeah, that's essentially.
Yeah. Okay.
You need to look at.
Thanks.
So I guess is the question asking whether if you didn't use the differentially private median, would you get a wrong answer for F2 estimation?
If the median computation would not have been differentially private, then the entire argument collapsed. So
Right.
Is that a function of the argument, or is it
whether it fails for the specific sequence with high flip number?
Whether there is a specific attack that fails this algorithm. That I'm not sure. I didn't try to fail the F2 thing. I mean, there isn't an attack in Omri's paper, the previous paper. They I think describe an attack of the F2, but I'm not sure if I do not remember the exact details. So I'm not sure if this attack would gives you what you want, but you can look it up there.
So I guess that we're kind of out of time here, so maybe we'll take further questions offline for Chaim.
Sure.
Okay.
Thank you again, Chaim.
Great. So I'm Uri Shtemer, and I'm from Ben-Gurion University, and I am a visiting researcher at Google, Tel Aviv. And what I want to tell you about now is kind of the impossibility results that were previously mentioned in this workshop in the previous talks. So it's a joint work with Chaim Kaplan, Ishai Mansour, and Kobi Nissim. Okay, and I'll be using exactly the same setup like Chaim and David, so I'll go over it real quickly, just so we are on the same page. So we have a streaming algorithm in the classical or in the Oblivious streaming model. The stream is fixed in advance, and we are thinking about a streaming algorithm that on every time step gets the next update in the stream and needs to respond with its current estimation for the value of the function that it is estimating. So it outputs its current estimation Z1, gets the next update in the stream, outputs its modified estimation, and so on. Okay, that's fine. What did we say that happens in the adversarial or in the adaptive streaming model? Now the stream is, we still have our streaming algorithm, but now the stream is not fixed in advance. Instead, we have some kind of an adversary maybe that chooses the elements in the stream one by one as time goes by, and his choice can depend on previous estimates that we give out. So on the first time step, this adversary chooses the first update. We respond with our first estimation for the value of the function that we are computing. The adversary gets to see this response. Based on that, chooses the next update in the stream, and so on. Okay, so exactly the same setup like in Chaim's talk and David's talk. And right, and the challenge is the same challenge. The fact that the choice for the elements in the stream depends on our answers in turn means that it depends on our internal randomness, and that's a problem. Okay, so still quickly, because still we've seen all of that in the previous talks. So here is a summary of kind of the transformations, the positive results that we talked about in the previous talks. So we kind of mentioned 3 different transformations that are able to take a classical streaming algorithm A and transform it into an adversarially robust streaming algorithm A. In all of them, the memory blowup depends on the flip number of the stream that we also mentioned in the previous talks. So we either have linear blowup in lambda or square root lambda blowup, or the accuracy parameter times lambda. And we also mentioned an impossibility results by Hart and Woodruff back from 2013, which where they showed that in general, linear streaming algorithms, they don't do very well in the adversarial streaming model. And that was a very strong negative result because first of all, their bounds are great. And second, a lot of the streaming algorithms that we like in the classical setting are linear. So their result kind of ruled out a lot of the existing streaming algorithms for the adversarial setting. But still, their result kind of left open the possibility that maybe still you can do everything in the adversarial setting, everything you can do in the classical setting, just maybe not using linear algorithms. In particular, these three transformations that are written here, they result in non-linear streaming algorithms. So what I'm going to show you now is that the answer is no. I'm going to show you a specific problem such that if you want to solve it in the classical Oblivious setting, you can solve this problem very efficiently with only polylogarithmic space. But if you want to solve it in the adversarial setting, then you are kind of stuck. And no matter what you do, no matter what algorithm you would try to run, your algorithm, if it solves this problem in the adversarial setting, it must use much larger polynomial space. And as it happens, the larger polynomial space that we need for that specific problem is exactly, or up till tilde, the root of the flip number. So if you look, the gap between these things here is like tilde, the square root of the flip number. So it kind of says that, well, I don't know if the flip number is the correct measure to look at, but if you decided to bound your space complexity blow up in terms of lambda, then in general, root lambda is what you have. Make sense? Okay. So the negative result that I'll be talking about now is based on a connection to the recent line of works on adaptive data analysis. So first, so let's pause for a minute and before we come back to the adversarial streaming model, and let's remind ourselves what adaptive data analysis is all about. Okay, and the way I'll present what adaptive data analysis is I'm going to show you, let's start with this warm-up actually, which is very similar to the, I guess, simple problems that Chaim mentioned in his previous talk. So here is something very basic that we all know. Let's say that we have some kind of an underlying unknown distribution D over a domain X, and we have some predicate H fixed that maps every element from the domain X to either 0 or 1. We know this predicate H, it's given to us. Our input is a sample containing n IID elements from the underlying distribution, and our goal is to estimate the expected value of that predicate over the unknown underlying distribution. Let's say we want to do it till some accuracy parameter alpha. And the question is, how do we compute our estimation and how good is it? Okay, so that's very super easy. We all know the answer. The answer is just compute the empirical average of the given predicate on the given sample. That's your answer. Return that as your answer. And by the Hofding bound, we know that provided that n is roughly 1 over alpha squared, your answer is going to be alpha accurate. Okay, so that's easy. So here is a slight tweak to this first warm-up. Nothing changes really. Now, the only difference is instead of one predicate H, I have K different predicates H1 till HK, but they're all fixed in advance. All of them are given to me in advance. My input is still a sample S containing n IID elements from the underlying unknown distribution D. And now my goal is to estimate the expected value of each of these given predicates over the underlying distribution. Okay, so nothing changes really. We are still going to compute for each predicate its exact empirical average on the input sample S, return that as our estimation for that predicate, and still by the Hofding bound, maybe with the union bound, we know that provided that n is roughly logarithmic in k, all of our answers are going to be very accurate. Okay, so that's easy, but the issue is that in order to apply Hofding bound in this setting, we needed to make sure we relied on the fact that all of the k predicates given here are fixed in advance. In particular, what we needed is that the choice of these k predicates is independent of the choice of the elements in our input sample S. Otherwise, Hofding breaks, the argument breaks. Okay, so great. Here is the basic formulation of the problem from the adaptive data analysis literature, or the ADA problem in short. And here what changes is that the predicates, the k predicates, are not fixed in advance. Instead, what happens is that I still get a sample S containing n IID elements from the underlying distribution. But now, in every round, I from 1 till k, on every round I get the next predicate, hi, and I need to respond with my current estimation for the expected value of that predicate over the underlying distribution. And the difficulty, as you can guess, is that because these k predicates are not fixed in advance, then we cannot apply the previous argument. This kind of creates dependencies between the choice of the predicates h1 till hk, so and between our input sample S. So what I'm going to do now is I'm going to say exactly the same thing, show to you again the basic formulation of the ADA problem, just with a picture. So here is the setting. I'm repeating myself. We have an underlying unknown distribution D. We have a data analyst. And our goal is to design a mechanism M that in the beginning of the game gets a sample S containing n IID elements from the underlying distribution. And that's the only interaction that this mechanism has with the underlying distribution. After this initial time step where I get the n elements in the sample, I don't have any more communication with the underlying distribution D. Now on every time step, the data analyst presents a predicate H, and we need to respond with our estimation for the expected value of the predicate H over the underlying unknown distribution D. The analyst takes that response and responds with the next predicate. We respond with our next estimation, and so on. Okay, so, and like we said, our goal is to design a mechanism M that ensures that with high probability, all of its k answers that it gives out are accurate with respect to the underlying distribution, with respect to the expected value of the given predicates over the underlying distribution. And the question is, the main question is, what is the size of the input sample that we need to get in the beginning of the game such that we can ensure that all of these good things happen with high probability? Now, when you first see this problem for the first time, you would kind of think, okay, well, maybe, so let's go back to our second warm-up here, where all of the k predicates were fixed in advance, and we could just respond with the exact empirical average. So here, responding with the exact empirical average worked fantastically. The number of queries k we can support could be exponential in the sample size n, which is great. So when you first see this problem, you might ask yourselves, okay, I understand that you changed the problem, the predicates are being chosen adaptively one by one, but maybe still answering with the exact empirical average, maybe that is still a good idea. But if you think about it for a little while, you would see that the answer is no. If you respond for every query with the exact empirical average, then that's a bad idea, and you could fail even on the second round. So in the first round, if you respond with the exact empirical average, you actually are not going to fail because the choice of H1 is in fact independent from the input sample S. But if you respond with the exact empirical average, you can easily show that even in the second round, you could fail badly. Okay, so that's a bad idea. Initially, I kind of thought to show you why is that a bad idea, but because we are a bit late on time, I'll skip that easy exercise. Okay, so what we just agreed on is that answering with the exact empirical average is a bad idea. It's going to fail even, it can fail even on the second round, but no worries, we can do other stuff. And here is like the current state of the art bounds on what we know that can and cannot be achieved for this problem of adaptive data analysis. So first of all, we know that if you care about computationally efficient mechanisms, then there is a mechanism, an efficient mechanism that takes a sample of size root k and answers k adaptively chosen queries. And we also know that, assuming one-way functions, this is the best you can do. If you want a computationally efficient mechanism that answers k queries, in general, you must take an input sample of size root k. But on the other hand, we know that if you are okay with computationally inefficient mechanisms, then suddenly you can do much, much more. Suddenly, k, the number of queries, can be exponential in the sample size n. Okay, so that's the current state of the art bounds for this problem of adaptive data analysis. What's the connection between that story and adversarial streaming? So what I'm going to show you now is kind of a reduction from this ADA problem that I presented to some problem in adversarial streaming. And so specifically, I'm going to present to you a specific streaming problem such that if you can solve that problem in the adversarial streaming setting, you can take such an algorithm that does that and use it in order to solve the adaptive data analysis problem that I presented. And therefore, you will run into the impossibility results of adaptive data analysis. That's what's going on here. And the streaming problem that we consider is defined as follows. We call it the streaming adaptive data analysis problem, or the SADA problem in short. So every update in the stream in that problem, every update UI in the stream is either a data point from the domain X, or it is a function mapping the domain element, the domain X, elements in the domain X to either 0 or 1. So every update, either a data point or a function. Our goal in the SADA problem is on every time step after we get the next update UI, we want to output an approximation for the average of the last given function on the multiset containing all data points that we have seen in the stream. That's the problem. So I think it's kind of clear, but here is a statement of the SADA problem a little bit more formally. So let's look at some time step I, and vector UI is the prefix of the stream of updates that we have seen so far. From that prefix of the stream, we denote by F subscript UI vector the last given function specified in the stream. And we denote by S subscript UI vector the multiset containing all of the data points specified in this prefix of the stream. Our goal is to compute or to estimate the average of this function F on this multiset S. That's the problem. Okay. So, okay, I understand the problem. Why intuitively should that be a good problem to look at when trying to show separations between adversarial streaming and classical streaming? So first, I hope we can all agree on the fact that if you want to solve the SADA problem in the classical setting, then you can do it very easily, because we don't need to maintain all of the potentially many data points that we have seen in the stream, because we can just use sampling. So we can maintain a small representative sample of all of the data points that we have seen in the stream. And now when you give me a function, I evaluate it not on the tons of data points that you gave me in the stream, I just evaluate it on the small representative sample that I'm maintaining, and that's going to be fine. What happens in the adversarial setting? In the adversarial setting, we don't have this trick of sampling. We know, because of the bounds on the adaptive data analysis problem, that in the adaptive setting, if you want to answer a lot of queries, your sample must be large. Your sample must be large intuitively. Your memory is large. You're not doing very well. Make sense? Okay. Great. So here is a more formal idea of the reduction and the analysis. So I'm assuming that I have an adversarially robust streaming algorithm A that solves the SADA problem in the adversarial setting, and I want to use it in order to construct an algorithm B that solves the adaptive data analysis problem. So the input to algorithm B, it's a data set P containing n points from some domain X. And now on every time step, algorithm B will get a query and it will need to respond with an approximation for the expected value of that query over the underlying distribution from which this data set P came from. That will be the goal of algorithm B. So the first thing that algorithm B does is it feeds one by one all of its data points that it has in its input sample P, feed them one by one to the streaming algorithm A. So we have kind of n updates here in the beginning. Every update I give to algorithm A a data point, the data points that I got as input. And now on every time step from 1 till k, algorithm B gets the next predicate and it needs to respond with its estimation for the expected value of that predicate. And what it does is algorithm B just feeds this function to algorithm A as a function update. Algorithm A gets this function as a function update, and it needs to respond with its estimation for the value of f on the collection of data points that we gave to algorithm A in the beginning. And I take this z, and that's my current response also. And here is the idea in the analysis. So if I want to analyze, I need to show that algorithm B solves the basic ADA problem. For that, I need to fix some underlying distribution D, and I need to think about what happens when I run algorithm B on a sample P containing n IID samples from this underlying distribution D. Now, by construction, if algorithm A works, its job in life is to guarantee that on every time step, its response Z is accurate with respect to the empirical average of the given function Fi on the input sample P. That's its job. But wait, that's not what we wanted, right? We wanted to ensure that our answers are accurate with respect to the underlying distribution, not with respect to the empirical average. In the adaptive data analysis problem, answering with respect to the empirical average, that's not a problem. I can answer infinitely many queries with respect to the empirical average. The difficulty is to maintain accuracy with respect to the underlying unknown distribution. So I have a mismatch here. But that's not a problem, because algorithm A, it's a streaming algorithm. It uses small space complexity. And as a result, also algorithm B uses small space complexity. And arguments from learning theory show that algorithms with small space complexity, they generalize. If you have an algorithm with small space complexity that computes an answer, Zi in that case, that is accurate with respect to the empirical average, then with high probability, this Zi is also accurate with respect to the underlying distribution. So we use such compression arguments to gap this mismatch between what algorithm A guarantees and between what algorithm B wants to achieve. Make sense? So that's very quick, but that's the idea on how do we show the reduction, and therefore can use the impossibility results that we mentioned for the adaptive data analysis problem. Okay, but there is some challenges that we need to handle in order to make this reduction and impossibility result work. And in particular, if you remember, the strong impossibility results for the adaptive data analysis problem, they assumed one-way functions, right? More than that, we said that if you are okay with computationally inefficient mechanisms, then in the adaptive data analysis problem, you can answer exponentially many queries. We would not get meaningful lower bound in our context from that. So what it means is that, as I presented it, this only kind of gets you to a computational separation, which is not what we wanted. We wanted an information theoretic separation. And actually what it means is that we cannot plug and play the negative results from the ADA literature as is. We need to open them up and modify them. But that's all I'm going to say about that. So, so I guess that the main takeaway from that slide is that we formalize this connection between adversarial streaming and adaptive data analysis, and we use we instantiate negative results from the adaptive data analysis literature into our context. Okay, great. So that's the next slide is going to be my last slide. Again, if you compute the details, you would see that the what we show is that every streaming algorithm that solves this SADA problem in the adversarial setting must use space complexity at least omega tilde root lambda. So the gap between polylog and root lambda is roughly root lambda, kind of matches for that specific problem the positive result that has root lambda blow up. And again, there are a lot of interesting open questions in this context, but maybe I'll just not mention them now, and maybe at the end of the workshop we'll say a few words on them. So I'll stop here.
Thank you, Uwe.
Thank you.
Okay, so I see
a question from Sayan.
Yeah. What is the space needed to specify the function fi as an update? You are absolutely correct. That's something that I've been hiding from you now. So in fact, you cannot have a single update that specifies a function. That's going to be way too much space for a single update. So in fact, what you need to do in the actual definition of the SADA problem, you need to like spread the functions that you specify over several updates. So it's not like a single update specifies a function, but like a collection of updates that specify a function. Make sense?
Okay. Yeah. Thanks a lot. Thanks.
So we have time for one other question.
Hi. So thank you for the talk. I remember from the paper, just saw it briefly, that there is also something for symmetric functions, like some kind of some adjustment of this SADA problem. So can you comment on this?
Sure. So like the current way I presented the SADA problem, it's not a symmetric function. But you can tweak it. You can tweak the definition of the problem such that it becomes a symmetric function. Like what was not symmetric here is that I said the last given function. But you can like also have for every function kind of an index that depends who is the last function, regardless of the time at which it appeared on the stream, and that would be fine. The only issue is that you remember I said that we need to open up the impossibility results for the adaptive data analysis literature. That part we don't know how to do after modifying the function to be symmetric. So right now, the state of the things is that for symmetric functions, we have a computational separation. And for asymmetric functions, we have an information theoretic separation. Make sense?
So that just means that for symmetric function, it holds for streaming algorithms that also like take that have some bounded time complexity or something like that.
Exactly. Currently, for
okay, thank you.
Thank you, Uri, and I guess we can continue to the next speaker. The next speaker will be Yeshwan Cherapanamandjeri from UC Berkeley. And so Chaim pointed out that the results until now are for scalar output, and he will talk about a result where the output is large and the kind. So this is not a streaming result, but it's it kind of points out what we what can we expect when the output is large.
Thanks, Omri. So let me just share my screen. Okay, hopefully everyone can see this and I can get started. Okay, first of all, I'd like to thank the organizer for inviting me to speak. So I'm Yashwant, I'm a grad student at UC Berkeley. I'm going to talk about some of the recent work we've been doing on building adaptive data structures. And this is based on joint work with Jelani Nelson at UC Berkeley. And so let me start with the general problem setup. So suppose you're given some data structural problem P. So here you should think of P as being some general problem, like let's say approximate nearest neighbor search, or as in this talk, it's going to be distance estimation. And this data structural problem accepts queries in some query set Q. So for approximate nearest neighbor search, it's probably vectors in some vector space. We say that a data structure D is a non-adaptive data structure for the data structural problem P if for all queries in the query set, the probability that the data structure answers the query correctly is at least 0.95. And this probability is taken over the random choices used to instantiate the data structure. The only problem with this definition is that this requires the query Q to be chosen independently of the randomness used to define the data structure itself. So in sequential settings where a sequence of queries could potentially be dependent on previous answers that the data structure has given, this assumption is no longer true. So a natural question that you could ask here is, can you actually handle dependencies for a lot of these data structural problems? And concretely, we want the following very strong guarantee. So you want to design a data structure such that for all possible queries Q, the data structure answers the query correctly with high probability. So now you can see in this definition that no matter how this query is chosen, the data structure still has to answer it correctly. So it's a stronger guarantee than the one on this line. In this talk, we'll focus on a specific problem. So we'll focus on the problem of distance estimation. So here you're given access to n vectors in RD, x1 through xn, which forms your data set. And you're also given a tolerance parameter epsilon. And your goal is to design a data structure, which when presented with the query Q, computes distance estimates di, which are 1 plus minus epsilon approximations to the distance of Q to each of the points in your data set. If you could do this exactly, for epsilon equal to 0, by just explicitly computing the distance of the query to each of the points in the data set, and this takes O of ND time. However, in high dimensional settings, you can do much better when the queries are independent of the data structure. In this talk, we'll only focus on the Euclidean setting. So all of the norms that we see and the inner products will all be Euclidean norms and Euclidean inner products respectively. Okay. So how would you solve this problem in the non-adaptive setting? So first you decide this threshold alpha So here, capital Phi is going to be the CDF of a Gaussian. So alpha is going to be the quantile corresponding to 1 on the Gaussian CDF. And next, what you're going to do is that you're going to draw approximately log n many random linear sketches with 1 over epsilon square rows, and each entry of each linear sketch is drawn IID from a standard normal. And you pre-compute the projections of each of the points in your data set with respect to each of these sketches. And now when you see a query Q, you're going to compute for each of these linear sketches the differences between the projections of the query and the data point. And you're going to get an estimate for each sketch to be the alpha quantile of the entries of this vector. And to aggregate these numbers over all of the L sketches, you're simply going to compute the median of all of these estimates. So you can see that you can perform this computation at query time in time O tilde of n plus d over epsilon squared. So the d over epsilon squared is simply to compute the projections of the queries, and the n over epsilon squared is to compute this quantile and to perform this median computation here. You can actually improve upon this runtime if you use faster approaches like the count sketch. And in fact, for this problem, we know algorithms which obtain the optimal space complexity, and this was done in this paper by Indick and Wagner in 2017. The question that we wanted to ask is, can you match these guarantees adaptively? So can you still do this when the sequence of queries are adaptively chosen, so they're not independent of the data structure? And the main result of our first paper was that yes, you can do this. So there is a data structure which gives you accurate distance estimates. So it solves the distance estimation problem with a query time of approximately n log n over epsilon squared. And its space complexity is nd over epsilon squared. So in our paper, we show that any algorithm which obtains these guarantees must have a space complexity of at least nd. So up to the epsilon squared, this actually matches the lower bound, and you can't expect a lower bound better than nd, I think, because in the worst case, you could just store all of the data points and you don't have an information theoretic lower bound anymore. Okay. So I guess now I'm going to step back a little bit and try to illustrate a general framework that will almost trivially give you an adaptive data structure. And then we'll instantiate specifically for our data structural problem of distance estimation. So suppose you have some non-adaptive data structure D, again supporting queries in some query set Q. You simply make approximately log of the size of Q, many independent copies of the data structure. And then at query time, you only sample, let's say, constantly many of these data structures, constantly many of these random data structures. And you query each of the sample data structure with the query Q, and you aggregate all of their answers. Usually the aggregation process will be pretty simple. You probably just need to take the median of all of the answers from these data structures. And you can show that this process produces an adaptive data structure with high probability. I guess one caveat here is that for problems like distance estimation or nearest neighbor search, this query set is possibly infinitely sized, but you could work over a net in this case, and it all works out. So how would you instantiate this for distance estimation? So you draw L of these linear sketches defined exactly as before, except now instead of L being log n over epsilon square, you draw roughly D of them. And what you can show is that if you take any vector v, so this entire process is scale invariant, so this is not an issue. So for any vector v, if you perform the estimation process by computing the projection of v with respect to the linear sketch and taking the alpha quantile of the entries of this projection, you can show that at least 0.9 of these L data structures actually preserve the length of v. So you could recover the length of v from most of these data structures. You can actually get tighter bounds on L for the Euclidean setting if you use some slightly more sophisticated techniques from this paper by Mendelssohn and Jaworowski in 2018. but a much more simpler approach, which is what we do for so we also have results for p norms between 0 and 2. And the way we do it is that we prove this property on a gamma net of the unit sphere. And then you can bound the errors. It's not too complicated. But now that you have a set of sketches that satisfy this property, how are you going to use this to do distance estimation? So suppose you're at query time and you're given some query queue. What you're going to do is that you're going to sample roughly log n many of these random sketches from the L sketches that you instantiated. You are going to compute a distance estimate with respect to each of the sampled sketches using the same procedure that we outlined before. You take the alpha quantile of the entries of the projection of Q minus Xi with respect to each of the sampled sketches. And as a final distance estimate, you simply output the median of all of the distance estimates that you obtained on the previous line. And again, here, since you only sample log n many of these sketches, actually projecting the query with respect to each of these sketches takes time roughly d log n over epsilon squared. And the median computation and computing all of these DJI estimates takes additional time n log n over epsilon squared. So the total time complexity is n plus d times log n over epsilon squared. So why is this true? So we know that roughly 90%. So if you used every single sketch that you had, we know that roughly 90% of them are accurate. So if you sample log n many of them, if you just use a simple Chernoff bound, we know that at least 60% of the samples are going to be accurate. And now you can simply perform a union bound. And so when 60% of the samples are accurate, the median is also going to be accurate. And once that happens, you just need to perform another union bound and complete the proof. And this is a very simple framework, but it extends to several other problems. So in our paper, we also did this for LP norms for p between 0 and 2 by using p-stable distribution instead of Gaussians. You can also do this for approximate nearest neighbor search. And we crucially use this as a subroutine to build an algorithm to build a faster algorithm for computing terminal embeddings. So you can use a subroutine to construct terminal embeddings in time sublinear in the number of data points. But now going back to the problem of distance estimation, a question that you can ask is, can we actually do better than the outline that I just showed you? So one big problem with this approach is that the update time of the data structure is very slow. So if you remember how we constructed the data structure, we sampled D of these sketches, and we computed the projections of each of the points in your data set with respect to each of these sketches. But since we have D of these sketches, the time taken to even project a single data point, to add even a single data point to the data structure is at least D squared. Because we have D sketches and each of them takes at least D time to apply to a data point. So now the question is, can you actually do better than this D squared update time? Okay, so I guess before we move on, let me just sketch the proof of the algorithm for the non-adaptive setting. And so this will be important because we will see which essential properties we need from this proof to build a better algorithm for distance estimation that does not use the simple framework we saw before. So here I have a restriction of the PDF of a standard normal distribution. So here we have the point 1, and simply from the way we defined alpha, the probability that a random Gaussian takes value less than 1 is alpha. And then we also have the 2 points, 1 minus epsilon and 1 plus epsilon. And simply because the PDF is lower bounded in this entire interval, the probability that a standard Gaussian takes value less than 1 minus alpha is alpha minus some constant times epsilon. And the probability that it takes value less than 1 plus epsilon is at least alpha plus the constant times epsilon. So if I just consider the random vector z, which is equal to pi times x, where pi is drawn by where pi is one of our random linear sketches, since each of the entries of z is itself standard normal, what you can show is the number of entries of z that are less than 1 minus epsilon is less than alpha, and the number of entries of z that are greater than 1 plus epsilon is more than alpha. So what this means is that if you take the alpha quantile of the entries of Z, then that is going to be a good estimate of the length of X. Okay, and then the rest of the proof is pretty simple. You simply use like a Huffding's inequality over like the log in many sketches. It gives you a high probability bound. And then if you take a union bound over your data points, like that gives you a high probability distance estimate for each of your data points. So the key point in this proof is that the only thing that you really relied on was the distribution of the entries of Z. You did not really care that this random sketch pi was actually drawn from a random normal. So you did not care that each entry was actually a standard normal random variable. All you cared was that the distribution of the outputs of the sketch are distributed according to a random normal distribution. So a natural idea that you could sort of use here is, a natural idea that would come to mind is, can I use a different family of random vectors instead of just using IID random Gaussians? And here, one option that you could pick is to use, I guess, what we call a randomized Hadamard transform. So instead of picking a sketch where each row is an independent standard Gaussian vector, you define your sketch as the product of a Hadamard matrix times a diagonal matrix where the diagonal entries are drawn from a standard normal. And a Hadamard matrix is defined in the following recursive way. So HD is recursively defined in terms of HD over 2. So HD is HD over 2, HD over 2, HD over 2, and minus HD over 2, and H1 is 1. So the neat thing about these randomized Hadamard transforms is that computing MV can be done in time O of D log D, simply because of the recursive structure. And signed versions of these randomized Hadamard transforms have previously been used to build fast algorithms for Johnson-Lindenstrass. And this was in this paper by Elon and Chazelle in 2009. Another nice property is that the rows of M, each individual row of M, are just standard Gaussian random vectors. The only problem is that the rows are not independent. So if I just look at the first column of M, all of them have the exact same entry. So there's no way that this matrix M is anywhere like actually close to a true Gaussian random matrix in distribution. But despite this, what we show is that if you pick roughly like 1 over epsilon to the 4 many randomized Hadamard transforms, and you looked at any vector V, and you computed the transformation of V with respect to each of these Hadamard transforms and looked at the distribution of the entries, they look approximately Gaussian. So the distribution of the outputs of this transformation are going to be close to the distribution of a Gaussian. And so if you want like epsilon accuracy, you need roughly like 1 over epsilon to the 4 many samples. So sorry, 1 over epsilon to the 4 many randomized Hadamard transforms. And I guess one thing to note here is that to simply compute this projection with respect to a single randomized Hadamard transform takes time roughly d log d. And since you have 1 over epsilon to the 4 of them, doing them all together takes time roughly like d log d over epsilon to the 4. So this does not have a quadratic dependence on dimension, which is where our savings come from. I wouldn't go into the proof of the statement itself. It has other applications to other problems like kernel approximations. But one thing that I'll just make a few brief remarks. So the Gaussian assumption in the definition of the Hadamard transforms we consider is necessary. So if you don't have Gaussians, you can pretty easily show that this property is not going to be satisfied. So even if you replace the phi by another distribution, like it's not going to be true. So let me see. Okay. So this property holds despite the fact that the rows of M are not independent. So despite the fact that like the rows of the Hadamard transform are not independent standard Gaussian vectors. And I think this is the first result where you analyze randomized Hadamard transforms when they're used to produce high dimensional embeddings, as opposed to like the low dimensional applications like compressed sensing or dimensionality reduction applications like Johnson-Lindenstrass. So how can you use this for distance estimation? So instead of drawing roughly like d many small linear sketches, you just use 1 over epsilon square, 1 over epsilon to the 4 many randomized Hadamard transforms. And the rest of the algorithm is pretty much the same. Since you know that the outputs of these vectors are distributed roughly according to a Gaussian, you still sample roughly log n many entries, and then for each of these data points, you compute, you sample these entries, and then you compute the alpha quantile of the entries. So this algorithm is nearly identical, and the proof is pretty much identical to what we saw for the non-adversarial setting. And as you can see, it only relies on some property about the distribution of the outputs of projections of vectors with respect to these randomized Hadamard transforms. So so this is a slightly suboptimal result. You can actually show if you did not rely on this like CDF concentration property, you could even do updates significantly faster than this. You could do d over epsilon squared instead of epsilon to the 4. Which we think is closer to optimum. And yeah, so far in this talk, we saw a simple framework to build adaptive data structures. We also showed that you could use much more fine-grained properties about like the analysis of the proofs of these data structures to build better algorithms. So we saw something that used randomized Hadamard transforms for getting faster update times. A couple of open questions are, can you actually build an algorithm with faster update times for LP norms? So randomized Hadamard transform works for Gaussians, and that works for the Euclidean norm, but that does not give you something for LP. Another open question is, we use a very strong notion of adaptivity, but suppose an adversary did not actually have access to the data structure. Could they do better? And could we show a trade-off between the number of queries and the space complexity you'd need under weaker notions of adaptivity? And can we get some of these like more fine-grained improvements for harder data structural problems like nearest neighbor search? So that's all I had for the talk. Are there any questions?
So thank you, Yeshwan. Thank you very much. Are there any questions?
Yeshwan, is there any hope of getting improved bounds for sparse vectors?
For sparse vectors, I am not actually sure. We didn't think about it, but yeah, I think that would be like pretty interesting if you could do it for sparse vectors.
Okay.
Okay, if not, then let's thank Yeshwant and all of the speakers again, and let's wrap up with a few minutes about some open questions and some concluding remarks. So Raj, yeah.
Yeah. Well, thank you so much, everyone, for coming, and thank you, Yeshwant, for your talk. So as you can see, there's been a lot of work that's been done just very recently, but there's still a lot of open problems. I think every speaker had some interesting follow-up questions and follow-up work. So for people who are either in the area or more junior researchers, this is there's clearly a ton of things that can be done. So there's a lot of exciting things that can come out of this. So what we've done is we've created a Google Doc with a collection of just some of the open problems that either were already sort of well established as open problems people had asked, or also the open problems at the end of each of the talks today. And we put them in this Google Doc, but I think feel free to, if you have your own open questions, to add one to the Google Doc with along with your name if you would like. I'm going to post a link to that in the chat right now, but it can also be found on the website. If you refresh the website, there's a link to the open problems there as well. So please do add any interesting questions you have, any interesting ideas or follow-up work, because there's a growing community that's interested in these types of problems, and it's useful, especially for people who are new to these types of problems, to get a sense of what the open problems are in the area. Do we want to discuss some of them, Omri?
Yeah. So if you have any comment, I think I think most of them were discussed during the talk.
Maybe maybe what I could do is I can just share my screen very briefly, just mention them very, very briefly for people that are interested. I know we are a little over right now, but for people that are interested, I can just share. Let's see, is this updated? Do we see the open problem page?
Yes.
Okay, cool. So, I mean, so a number of like sort of basic higher level questions on the first page. As we saw like many times throughout this workshop, many times it was the quantity these papers study was this lambda quantity, this flip number. And in some sense, the flip number measures the number of times that you really need to change your answer if you want to continue to be correct. And it has sort of a nice connection in that way to adaptive data analysis, because the number of queries in adaptive data analysis, because every new query, well, you better answer the new query. Similarly, when the flip number changes, the function goes up by 1 plus epsilon, you better switch your answer in a stream. So there's reasons to believe that that's sort of an interesting quantity to study because of its connection to adaptive data analysis. But it's not clear that this is the correct quantity in terms of space complexity of, say, general functions in insertion only or even turnstile streams. So it's possible that by looking at another quantity, there's maybe a more correct, a more comprehensive view of what the property of the function that we're trying to estimate is. And so perhaps by giving more information than just the flip number, some more generic quantity, we can get bounds that are more general, like for arbitrary functions. So it's not clear that the flip number is the correct measure to look at. So this is more of a high level question. And as was already mentioned, some of the results we've discussed were usually for just scalar value output. And for some problems like the heavy hitters problem, where you need to output a set of coordinates, well, for this problem, it's relatively easy to show that you can get adversarially robust algorithms for this just by using robust algorithms for L2 estimation and only changing your set of heavy hitters when the L2 goes up by a factor of 1 plus epsilon. So for that reason, like some problems, it's easy to put them within this framework of scalar valued output, even when they're not a priori scalar valued, like heavy hitters problem. But for some problems, it's not clear. Well, there's no clear reduction. There's no clear relationship to a scalar valued quantity. And so for this case, there's interesting. What is like the right parameters? What is the right way to look at these problems in a generic way, similar to the way that we have these results to give generic transformations. And I'll go through the other ones a little bit more quickly, but I do want to mention that one of the major open problems that I think David mentioned in his talk was this problem of turnstile streaming. So the two transformation results, the differential privacy and the one in David's talk, both of those, they did hold for any possible stream. It could have been a turnstile stream. The issue is the spatial complexity depended on this flip number thing. And of course, as he mentioned, you could insert and delete. And so the flip number can be as large, it can be unbounded in the turnstile model. So a priori, for most functions, you don't get a bound on the space for the turnstile model. But like one question is, can we do anything in the turnstile model for the standard streaming problems that people have been studying for 20, 30 years? Can we get any sublinear space algorithms to these problems in the turnstile model? And so probably the most one of the most popular ones, one of the most famous functions is the F2, the L2 norm of the vector. So the question is, can we design sublinear space L2 estimation algorithms in the turnstile model? So this is like a major open question in the area. And as was alluded to again in this workshop, a paper of Hart and Woodruff showed that for a certain class of algorithms known as linear sketches, any randomized function of a linear sketch, this is not possible. There's an adversary that works against this. So in some sense, there's some details to be checked in the reduction, but more or less this applies to the streaming model as well if your algorithms are linear sketches. So there's some reason to believe that this is hard, but this is for general algorithms that are maybe not linear sketches. We don't know how to prove a lower or improved upper bound for this problem. So this is a major open task. And lastly, I forget if it was mentioned, but if you want to solve this problem deterministically, F2 estimation, it's known from the same paper of Alla, Mateus, and Segedi that you need omega n space. So currently the best known upper bound is omega n, and there's no lower bound other than the oblivious lower bound. And lastly, we want more separations. Just a number of other questions here. We can ask about other adversarial models, or whether we can get improvement separations for like certain types of asymmetric functions. I don't know, Uri, if you wanted to say something about this, you had mentioned it in your talk.
Yeah, so as I mentioned, the current state in our impossibility result is that we have a symmetric function for which we show computational separation. So if you want a computationally efficient streaming algorithm, then you cannot have one in the adversarial setting, but you can have one in the classical setting. But for asymmetric functions, we are able to push it towards an information theoretic separation. So yeah, so the question is there an information theoretic separation for symmetric functions?
Thank you. Yeah, so there's a number of questions that we can ask on different types of functions. For example, these asymmetric functions. I'll just say what I answered in the chat a moment ago. One thing I didn't mention about this linear sketching thing is there is a known connection between linear sketching algorithms and turnstile algorithms. In particular, there's some conditions under which all turnstile algorithms can be transformed into linear sketches. It's important to know that this doesn't say anything about our current question, because this transformation is for, it's an equivalence for the non-adaptive, the oblivious static setting. So it's not clear that any adversarially robust turnstile algorithm can be made into an adversarially robust linear sketching algorithm.
Let me also add one thing about that, which is that this reduction, this lower bound proof in the work with Hart that we have, it crucially uses that the inputs can be real numbers, and it uses rotationally invariant properties of Gaussians in multiple places. And when you try to discretize the argument to get lower bounds for linear sketches with finite precision, the argument just breaks. So so there is some gap there as well.
Yeah, I think I mentioned there may also be some question about whether if your outputs are if your algorithm adaptively changes, like your algorithm could be adaptive in the same way that the adversary is adaptive, but it's not clear whether that helps either. So this is really maybe a little bit less of a formal connection, more of just sort of a reason to believe that this problem might be hard. And lastly, these two questions kind of go together hand in hand. Whether we can consider other adversarial models that are perhaps weaker than the most general model we considered here, but which still are able to model some of these motivation areas that we talked about. For example, like recommendation systems, where we're getting recommendations from users and modifying their output in an adaptive way. Well, there's no adversary there, but it's still adaptive in some sense. So there are other models which can sort of capture what we care about, but are not as strict as the model that we've been studying here. And of course, along with that is whether, one model is to assume that you do have an adversary, but it's cryptographically bounded. It has bounded either resources in some sense. There's some results on this task. If you assume, for example, for F0 estimation distinct elements, we can get improved bounds if you assume the adversary satisfies certain cryptographic assumptions and has limited computational power. But by and large, there's still, I'm sure, more work to be done here. So, and then at the end, we just pasted the open problems from each of the 4 talks that we had today, or 5 talks rather. So on these pages were the open problems from at the end of the slide. So feel free to go through them. But what I'll do is this Google slide is open, so please go ahead and if you have additional questions, feel free to add them to this slide. Yeah, anything else? Omri? I think.
Yeah, I think it's all good. I think there are also other open questions, but the list goes on. But yeah, I think this is a good start.
Can I ask one last question? Hello?
Yeah, go for it.
Yeah, sorry. This is a non-technical question. Will the video recordings be made available later on in the web page?
Sorry, say that again.
Will the recordings of these talks be made available later on?
I'm not sure. I believe so.
Yeah, I hope so. I mean, it is recorded by STOC organizers. If they're willing to release the recordings, then they will appear on the website.
Okay, thanks.
Yeah, I don't think we have the recordings, but I think, yeah, I imagine that they will be because it is being recorded.
Yeah, thanks.
Okay, well, thank you all so much for coming. I can stop the share now, and yeah, I hope this generates some exciting future work, and yeah, I hope to see you all again at future results that we hope to we don't even know about yet on this area. So thank you all.
Thank you, everyone.
Bye.
Bye-bye.